Okay, so I hope you can see the screen and hear me. So the the lecture today is to discuss the topic of adjoints, and this is specific to self maps, meaning you have a linear map T from V to V. V is an inner product space. So in that context, we can actually define a map T star again from V to V. Okay. And so initially, if you are a bit confused regarding this notation, just stay with me and you'll see everything being validated. We have already seen that given a map from V to W, there is already a T star from W star to V star. So it's the same notation, but you see the where it connects and where it doesn't and so on. So just treat it as a separate T star for now, and then we'll connect it with the two concepts. The one you have seen earlier, the dual of a map, and this is now going to be the adjoint in the presence of an inner product on a finite dimensional vector space V. Okay. So we have a finite dimensional inner product space V, and for each V, we have a linear map, this one, right? Remember, so this thing, I'm choosing this particular thing because this is going to help us conclude that this is linear, as I've said here, right? Typically, why? Because this inner product is linear in first variable, right? And this is usually if I'm working over C. Okay? This is antilinear or conjugate linear in second variable. Okay? Again, this F is R or C. If I'm working over R, it doesn't matter, it's bilinear, it's linear in both slots. If I'm working over C, this is antilinear, and I want the map to be linear. So that's why I'm putting dot V as opposed to V dot. Okay, that's the only consideration. But otherwise, just so this will always work, whether it's R or C. So we have a linear map from V to F. So in particular, this is going to determine, so this element determines an element of the dual space, right? Correct? All right. So what is it saying? It's saying that given an inner product, you can define this map from V to its dual, where little v goes to this map. Okay. And if you ask, okay, is this a linear map? What would be your guess? Well, it's additive. That part, that part is clear. But if I scale v by lambda, this on the one hand goes to this map, right? So this means given a w, you take w dot lambda v. But remember, this is typically lambda bar dot v, correct? On the other hand, if I take this map and multiply by lambda, so if this is my capital Phi, let's say, right? So capital Phi of lambda v is this map, lambda bar of this map, which is lambda bar of capital Phi of v, right? And this need not equal lambda in general. Of course, this is in general, but of course this is, so if lambda belongs to R, even in the context even if F equal to C, but since we want it to be linear with respect to the base field, it's natural to work. And of course, if F equal to R, then of course this works, because over the reals there is no bar, so lambda bar is lambda. So this is an equality in our case. If we're dealing with, say, real inner product spaces, this map is a linear map. Okay, the only thing I'm pointing out is this map is a natural map, but this map is not going to be a linear map. If you're working over complex numbers as a base field, it's going to be antilinear. So scaling v by lambda and then taking its image is the same thing as taking the image of v and then scaling by lambda bar. So over C, this map is antilinear. Over R, this is a linear map. Okay, so is this clear? Okay, so all right. So we have a map, V goes to dot V, which means this to be interpreted again. So this, you should interpret this as saying, what does this do? So given a W, this is going to be simply by definition this. Okay, that's what this map does. Okay. So it's additive, that much is clear. So you can check this very simply, and it's also, and if phi of, and it's injective, because if phi v of v1 equals phi v of v2, then w dot v1 is w dot v2 for all w, but that means that v1 equals v2. We proved this last time. In an inner product space, if a dot product with one vector for any arbitrary vector on the other slot equals dot product with v2 for the same arbitrary vector, then you can simply write this as w dot v1 minus v2 is 0 for all w. You plug in w equals v1 minus v2, you conclude that length of v1 minus v2 is 0, but that implies v1 minus v2 is the 0 vector. Okay, so this implies that phi is an injective map. Okay, it's additive, so phi is in fact phi v is an additive map. So capital phi v of little v1 plus little v2 is capital phi v of v1 plus capital phi v of v2. So you can ignore the v here for the moment. This is really a capital. This capital phi is determined by the inner product. Okay, so if you want, you can ignore this v. It's an injective map, and it's surjective because of. So the point is, let's work over real spaces so that we don't have to worry about this map being linear or anti-linear. This map will be linear. Okay? So the point is, this map will be linear because if I scale v by c, I get a map dotting with cv, but then over reals, I can pull out the c, and this c times dotting with v. So this will be a linear injective map, and I'm claiming that this map phi, capital phi, okay, since here I'm calling it capital phi, this capital phi is a surjective map. So this capital phi gives you a very natural isomorphism, linear isomorphism between v and v star, provided v is a finite dimensional real inner product space. And the map is simply given by saying v goes to this. So at this point, you might object saying, well, didn't we say earlier that there is no canonical isomorphism between v and its dual? Yes, there isn't, and I'm not claiming this is canonical. This is natural only when you have chosen an inner product. The choice of an inner product is not a canonical choice. There are many inner products, and to construct an inner product, typically you end up with the process that you start with the basis, define an inner product with respect to the basis vectors, and then extend it to all vectors. So the choice of an inner product invariably will boil down to the choice of a basis, but an inner product is a different thing than a basis anyway. So once you are given an inner product, which may appear very naturally in the context, you do have this natural linear map, v to v star, which is an isomorphism. So in that context, it's slightly different from saying that v to v star is not canonical isomorphic. They are naturally isomorphic if v is equipped with an inner product. And again, everything is over reals. If you do this over complexes, then this is going to be an antilinear isomorphism, meaning scaling by lambda means you pull out lambda bar. Okay. So before I show the statement, is the context clear? Are there any questions?
Sir, what is the difference between the little v star, dual of a vector we had defined, and this, empty inner product thing? The dot v, this thing.
Yeah, that is different. See, the little v star is entirely dependent on a basis, right? So how did you define v star? So v star it's not as defined as such. So the point is to choose e1, e2, en, and then this allows you to define e1 star or en star, right? So that is what it is, right? And so the point is, because what is ei star? Ei star by definition acting on summation aj each is ai. Right? That was a definition. And then if your v is summation ci ei, then you declare your v goes to v star, this to be summation ci ei star. This was the map from v to v star. Right? So this is just starting with the basis, you just do this. So this has nothing to do with this v. They're entirely different things.
Okay, sir.
So if you ask, okay, fine. So suppose we have this, so you see this shortly. So if you see this, in fact, in the proof here, that if you somehow were able to choose EIs to be an orthonormal basis with respect to this inner product. So whenever you're talking about this inner product, suppose EIs are not an arbitrary basis, but an orthonormal basis, which you can always do by choosing a basis applying Gram-Schmidt, for example, right? So suppose these were an orthonormal basis, then it will turn out that this V star in that context is precisely this one, the one you get from here. Okay. So yeah, so hopefully you'll see that in the proposition. So as such, they're not connected. So this inner product might have nothing to do with the basis you choose to define V to V star. They might just entirely be, so the basis you choose, EIs, may not be orthonormal with respect to this inner product, right? So this map dot with V might typically have nothing to do with the other map. See, the other map depended on a choice of a basis. This map depends on the choice of an inner product. So if the inner products and the basis are not sort of nicely compatible in a certain sense, you do not expect the image of little v under this map to equal the image of little v under that map. Okay, is that clear?
Yes, sir.
Yeah. Are there any other questions? Okay, so this is what I'll call the finite dimensional Rees representation. You'll see grand, like grander variants of Rees representation in the special lecture on Saturday, because any talk on dual spaces will invariably lead to measurements and measures. I mean, there's no way around it, one way or another. So some of the things you'll see may not make sense immediately, but they will make sense in a year or a year and a half. So this is the one which does make sense to us immediately. It's called, I'm calling it the finite dimensional Rees representation, because the general family of Rees representation theorems are typically for infinite dimensional spaces and in an entirely different context, which is beyond linear algebra. It involves analysis. Okay, so what does it say? It says that let V be a finite dimensional inner product space. Again, let's say over the reals. If T V to F is a linear map, so what would you expect? You're saying that I have a linear map from V to F. So by definition, this T is an element of V star. But we already know that because this capital phi is an isomorphism, okay, I mean, at least you'll follow from this theorem, we already have such kind of linear maps, right? So here on the one hand, you're saying that I have a T, this is an element of V star. On the other hand, I also have this. For some little v, for any little v, these are also elements of V star. So it would be nice to claim that for any element in the dual, there is some little V0, so that T is of this form. Then that would prove that in fact this map is an isomorphism, right? And that is precisely what this finite dimensional Rees representation claims. It claims that whenever if you give me an element of V star, it's by definition a linear map from V to F, then I can find a V0. In fact, it will be unique because of this being injective, but there is some V0 such that the map T is given by inner product of the input variable of T with this vector V0. So if you think about this equation is saying that T of dash equals dash V0. So in other words, saying the linear map T is identical to the map that we are calling this thing, right? Which is nothing but capital Phi of V0. In particular, this is saying that this map is onto. Okay? It's already linear, it's already injective, so it will be a linear isomorphism. So in fact, it's saying that given an inner product, there is a linear isomorphism from V to V star, which is given by simply this this method.
But doesn't rank nullity imply it is surjective?
Rank, oh yes, okay, yes, it's fine. I see. You find it easier. Yes, certainly. Yeah, so you can use rank nullity once you know it's injective and you know the dimension of V star is this. Yes, right. So you can use that as well. But I mean, this theorem still stands in the sense it's saying that so you can use if you want, you can use rank nullity and hence claim that any element of T is of this form precisely. So in fact, I'm going to tell you how to compute this V0. So if I give you a T, how to compute the V0. So the proof of this theorem is literally going to be an explicit one in the sense, given this T, you actually construct a V0 and then you check that T is inner product with V0. So yeah, you can also prove that phi is an isomorphism and hence claim that this Rees representation is true by rank nullity. Certainly, yes. But let me give you the proof.
This is a constructive proof you're saying.
Yeah, so given this T, you'll be choosing some basis, make it orthonormal, and then you can construct V0 out by evaluating T on certain vectors. So which, if you really think about the rank nullity and all of that, if you unravel all of those proofs to its bare bones, you'll probably end up with the same proof here. But in some sense, the point is you build certain things so that certain steps are easier rather than going through the thing through first principles. So if you unravel the rank nullity and all of that, you will end up probably with the same kind of a proof, but that will be a longer proof. The rank nullity will tell you that phi is an isomorphism, and with a little work, this theorem is true. And so the proof of this theorem is directly by constructing this V0 from T and some auxiliary choices. Yes. And this in particular implies that phi is surjective, which, as you pointed out, also follows from rank nullity. So, right. Okay, so is the statement clear to everyone? So it's a very nice statement. So it's saying every element in the dual comes from inner product with some V0, and in fact with a unique V0, because this map phi is an isomorphism. So every element in the dual, it's like this bracket thing, that every element in the dual is like dotting with the sketch vectors. So you get a scalar. Are there any other questions? Okay. Yeah, so we start. So remember, I mean, what is the starting point? In most of these things, when you deal with inner products, you start with an orthonormal basis. So you might say, well, how do we produce an orthonormal basis? And this is what I've been emphasizing over and over again. We have done all the hard work. Start with any basis. Well, how do you know there's a basis? Well, it's a finite dimensional vector space. Start with one non-zero vector that's linearly independent. Keep adding one more, and by replacement theorem, you're guaranteed that this can be extended to a spanning set, which is linearly independent. So it is a basis. Fine. Now, given that basis, you can use Gram-Schmidt, and you can orthogonalize the basis, and then you can normalize the length of the vectors to produce an orthonormal basis. So all the steps are very concrete, and you can do them. Okay, I mean, given a concrete examples, we have seen many in class as well. So straight away, I can assume that there is an orthonormal basis because I know the steps to produce an orthonormal basis. I find a basis, orthogonalize, and then normalize. So start with an orthonormal basis V1 through Vn. Okay. Now the point is, this is something we saw last time. We use this in what's called Bessel's inequality. That whenever you have an orthonormal basis, you can always explicitly write down any vector. You can always write down V as a combination of Vi's, but how do you get the Ci's? Well, the point is, Ci's are precisely V dot Vi, because I can just write V as C1, and this is something we proved last time, right? It's pretty easy. Cn Vn, and I can take V dot Vi, because Vi's are on orthonormal basis. The only thing that survives here is Ci, because typically I'm going to get Cj Vi Vj, that is delta Ij. So this is Ci, so I'm done. So I just put this back in. So this is, it's crucial that it's orthonormal. So I can always write V as V dot Vi Vi. It will not be true if I do not have an orthonormal basis. Okay. And this is literally what I explained last time. This is the force decomposition diagram. Given an arrow representing a force, you break it up into its perpendicular components. It's literally that. Okay. Fine. So now I can apply P to this. So if I apply P to this side, see, by linearity, what will happen? It will be T of this, but that splits up into T of V1 plus plus T of Vn, right? But because T is, so this is the additivity part of T being linear, but then I can pull out the scalar, so I get this. Great. So what is this saying? This is saying that T of any arbitrary vector. So you realize what this is, right? So this I can rewrite in a different way. So can you think how I can rewrite this? So this is a scalar now, right? Because T was an element of the dual. So I can put the scalar not in the front. I can put the scalar in here, right? I can write this as V T V1, correct? Isn't it? So this is one of the nice tricks with bilinear sort of forms or inner products. You can pull out the scalar from the first one, put it into the second one. It doesn't matter, right? It's a very nice trick, and you can use it in things as advanced as Riemannian geometry, tensors, general relativity, or things seemingly as simple as linear algebra. So I just put it in there. But now do you see what to do from here? So I have V dot something plus V dot something plus V dot something. So the first entry is always V. So what can I do now?
Entry is constant, so that vector we can.
So this is just linearity in the second slot. Remember, inner product is additive and additive in both the slots, and it's linear and antilinear scalar. So this is V dot this quantity, right? Is everybody okay with this? But you see, what is this telling you? This is telling you that TV is V dot this thing, right? And this thing is independent of V entirely. So given V, any V, T of V is inner product V with this vector. So this is what I call V0. So given my T, I simply start with an orthonormal basis, apply TV1, multiply by V1, dot, 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 apply TVN, multiply by VN, add them all up. I declare it to be V0. And by construction, I see that T of dash is dash with V0, right? And this is precisely what I wanted. So what is this V0? This V0 is nothing but this quantity entire, okay? So in fact, to realize something more, not only is there a V0, but what you're saying is this V0 is independent of the choice of the orthonormal basis, which is something which is used in, say, quantum field theory, for example, or even in curvature in geometry many, many times. So it's saying that this quantity is independent of the choice, because I could have chosen another orthonormal basis, right? Wn, orthonormal basis. And I could have considered this quantity. And this is also going to be equal to V0. So that's the amazing thing. That T is given, the inner product is given, and then you choose an orthonormal basis, evaluate T, and then multiply with the corresponding basis, add them up. This final quantity is in some sense like a universal vector associated to T and the inner product. It does not depend on the input orthonormal basis you choose to compute this with. So that is my V0. And it's clear by the construction that T is inner product with V0. So I mean, I'll show you the formal steps in the slide, but is the setup and the general idea clear as to what we are trying to do here? Any questions? Just think it through. I'll pause. It's a very short proof. It's a slick proof, but I mean, just store it in your head as an important sort of idea here. So we are not going to use later on this fact that this expression of V0 is independent how you compute it, but this is used in many instances as I indicated. Okay. So yeah, so yeah, so here I gave the proof using assuming I'm doing it over C. As I said, we'll stick to R, so then there's no bar, so there's no conjugate. So these are all real numbers, so the conjugate is nothing. But in general, if you put the scalar in the second slot, you have to put a conjugate because it's antilinear in the second slot. But the same idea persists because it's additive in the second slot. I can add all of these things together, and so my V0 is simply going to be this vector. So T of any vector V is going to be inner product V with this vector V0. So it works over the complexes, it works over the reals. Over the reals, I simply have TV1, V1 plus dot dot TVN, Vn. And this is one way of computing V0. You could have started with any orthonormal basis. In particular, you're proving that this expression is independent of the orthonormal basis you choose to compute with. All right. Any questions or thoughts? Any clarifications? Okay. Okay, so now let us, so this is just saying that you can identify V with V star using this proof or actology, whatever. And that's one of the things, that's the takeaway from the first two slides. Given an inner product, there's a natural identification between V and V star. All right, so now let us go back to the dual space and the dual maps and so on. So given a linear map from V to W, there's a dual map from W star to V star. And recall how it was defined. So just one sec. So how was it defined? So recall that if I have a map L here, I want to give a map from V to W. So L, remember, was a map. So L was a map from W to R, let's say. I have a map from V to this is T. So naturally, if I compose these two, I get a map, right? This is L compose T, right? I first apply T. So this is the map, right? This was what T star was. Given a linear map from W to R, you pre-compose with T. That's now a linear map from V to R, and this was defined to be the dual. And we in fact had checked that if you choose a basis, write down T beta gamma. Then if you choose the dual basis, write down T star gamma star beta star. These matrices are transposes of each other, right? Or conjugate transpose. Okay, so now we're in the presence of inner product spaces. This is just a recap. So now we're in the presence of finite dimensional inner product spaces. So V has an inner product, W has an inner product. Okay, great. So remember, because V has an inner product, we have a bijection or a linear isomorphism or whatever you want to call it from V to V star. So the easiest way to think of this is this diagram. So you have a map from V to W, right? On the other hand, we have this capital PV. So this is a bijection, correct? And we also have this map, the dual map. This is the dual, right? This is capital P of W. Okay. So I hope there's no confusion. V has an inner product, W has an inner product. They're just different inner products because V and W are different spaces. This is the identification we talked about in the previous slide. So this is a bijection, and we have this T. Okay. I'm not making any claims regarding this commutativity of this diagram or anything, whatever that means. But so far we have this identification. Over the reals, this is a linear isomorphism. Over the complexes, this is an antilinear isomorphism. Same here. So let's say we are doing everything over the reals. This is a linear isomorphism. This is a linear isomorphism. You have the map T. You have the dual map T star. Okay. So now that you have the dual map T star, so you realize one thing. Given this map T from V to W, you could always produce a new map. You could always look up. You could always produce a new map from here to here. Can you see what this new map is? I'm asking whether you can spot a new linear map over the reals from W to V. T inverse does not make sense. You cannot say T inverse.
5V 5V compose T star compose 5W.
Well, one of the arrow has to be inverted, right? This one, for example. So
Yes.
I can go down, go left, but then I have to go up. But then I can invert because this is a bijection. In fact, over the reals, this is a linear isomorphism. So I can always consider this map, capital PW. These kind of diagrams are very, very commonplace in modern mathematics. So 21st century mathematics, you would have to get used to such diagrams. So might as well see it now rather than see it later. Okay. And then you have to put V inverse. Right. This inverse makes sense. All of these vertical arrows are invertible because they are bijections. Over the reals, they are in fact linear isomorphism. Even otherwise, they are bijections. So I can always invert it. So this is a map from W to V, right? So the advantage of having an inner product is I'm not making a random choice to get from V to V star, because typically to identify V to V star, I have to choose a basis. I'm not making that choice. I'm already in the presence of an inner product. So I use that to get a natural identification of V and V star. Same here. So given such a linear map, I can always go from W to W star by this identification, use the dual, the classical dual, and then use phi V inverse to get a map going the other way. This, of course, will not be the inverse of T because T might not even be invertible to begin with. This is just a map, which is the wrong way map, so to speak. You can get by using these identifications, the vertical identification. So our job for this lecture is going to be focusing on the very specific case where W equals V. So both W and V are the same. So if V equals W, you're dealing with self maps. So these vertical maps are the same identifications. V to V star, V to V star. T star is the map induced from V star to V star. So in the context when W equals V, what is this map related to this map? Because at the end, see, to define this map, you need to put the classical dual map T star. And these are just nice bijections. So our aim would be to understand this map in relation with this map and this map, T and T star. Okay. So that's what we're going to do. But I just wanted to set up the background. So hopefully, when you see this diagram, you shouldn't scare and be concerned. I mean, this diagram is simply there, whether you like it or not. Okay. And obviously, I cannot sort of start with T here, go here, and that's an isomorphism. No, I mean, T could be the zero map, in which case zero map followed by anything is still the zero map. It's not that if I go to the right, go down, and go left, this is this map. It's not. So it's just a square which is there, and we're trying to make use of the vertical arrows being invertible or linear isomorphism so that we can define this new map from W to V. Typically, the dual is going to be a map from W star to V star. Here we get a map from W to V. And we're using crucially this identification. Okay, so no choice of basis involved, but you are assuming there's an inner product on both V and W. So that's a choice. But suppose it was given to you or made for you, then this isomorphism is natural. All right. So any questions, vague or otherwise, before we proceed? So if you have any questions regarding why we're even doing such a thing, it will be clarified in a moment. You'll see the relevance and importance of this soon enough. So the classical dual is nice, but it is what it is. It has its limitations. But if you are in the presence of an inner product, which is mostly the case in physics and geometry pretty much all the time, then this is the map that you want to look at, not T star. Okay. This map from W to V. You'll see why. Okay.
When V equal to V, will it form like a sort of change of basis?
When W is equal to V, you mean?
Yes.
Well, so no. So which one do you mean is change of basis?
I mean phi inverse compose T star compose phi V. This.
Well, I see. Well, not quite in the sense. See, the point is this phi is going from V to V star, right? So V and V star are not naturally, not canonically isomorphic. So you're sort of going to V star. So this map is still the dual of. It's like a more palatable representation of the classical dual. The classical dual lives in the dual spaces. This is living in the original spaces, so to speak.
Okay.
So yeah, but it will be related. We'll see how the matrices are related and so on. But it's not exactly the classical dual simply because the domain and the range of the codomain of the classical dual is not the domain and the codomain of this map. They're obviously not the same, right? So that's a distinction we have to keep in mind. No matter how much you try, V and V star are not canonically isomorphic. They are different spaces containing different entities. No matter how clever an isomorphism that you define to connect it, they are different at the end of the day. But we're trying to make sense of how different they are, whether there's a natural sense in which you can, or connect things together. So that's where this is getting to. Okay. Yeah. So let me set it up. So yeah. So given this map T from so as I said, given this map T from V to W, you can define this map T V inverse compose T star. So this is the classical. So let me put a bold here. Okay. So the bold means this is the classical adjoint, the one we know. Okay. So this let me just correct. So this one is going to be this map. We start with the natural isomorphism given by the inner product, go from W to W star. It's a bijection even over C. Apply T star and apply the inverse of the bijection phi V, and you get a map from W to V, and we define this map as the adjoint of T. Okay, this is what it is. Okay, So you might ask, okay, why is this linear? So over the reals, it's clearly linear because T star is linear. This is a linear isomorphism. This is a linear isomorphism. What about C? Will this be a linear map over C? So it's additives because all the phi W, phi V, T star, they're all additive maps. It's the scaling that's under consideration. If I scale by lambda, will lambda bar come out or lambda come out? If lambda comes out, then it's a linear map even over C. But remember, over C, this map is antilinear, right? Over C. So the point is over R, adjoint is linear, right? Because it's a composition of linear maps. Over C, what happens? If I take a W and W will go to something, right? If I whatever, but if I scale W by lambda, what will happen under this map? So if I scale W by lambda, this map is antilinear, right? So what I'll get here is lambda bar of capital P W of W, right? Because this is antilinear. Now I apply T star. See, T star is linear, there's no issues there. So this is lambda bar T star composed capital P W of little w, right? And then I apply this. But remember, this is antilinear, so the inverse is also an antilinear map, right? So if I apply phi v inverse, lambda bar will come out, correct? Times capital phi v inverse composed T composed PW of W. But what is this quantity? This is precisely the adjoint of T acting on W, and this is precisely lambda. So this is a linear map, even over C, right? So I hope you get the point. So over R, it's clearly linear, but over C, it's linear because you have two antilinear maps. And so the antilinearity is killed because you're composing with both of them. Okay? So no matter which field you work in, this map, the adjoint of T, is a linear map from W to V. So it's a bona fide linear map. No issues over R or C or whatever. Is this clear? Is this the thing that I explained? Again, as I said, we are not going to make much use of examples over C. But it's good to know the theory when it's sort of being done in this generality, that it's done because it works over both R and C, although there are some steps which are slightly different. Any questions? All right. So, great. So now let us see what this actually means, because this is like a lot of maps. Okay. So phi v is additive but skew linear or antilinear. So phi of CV is dot CV, which is C bar comes out because it's skew linear in the second slot, which is C bar phi v. That's what I mean by skew linear. It's clearly additive. Adjoint is a composition of three additive maps. So it's additive. T star is additive, phi W is additive, phi V is additive, so phi V inverse is also additive. What is T star on this? Well, T star is linear, so this is not an issue, right? So it's just this, okay? So yeah, so the point is that T star, this is something you can check very easily. But what I'm trying to say is this map, because it's a composition of three maps, two of them being skew linear, the total thing is linear. That's what I'm trying to write out here, which is if you unravel, put a V here, you'll see that this is precisely what I did. Okay. So, okay, anyway. So what I'm trying to do is, I'm trying to do the following. So remember, if you just think of this map, what does it do? So what is phi of W? Phi of W is W goes to dot with W, right? Correct. This is the map. Now what does T star do? So remember, so this is what you're trying to compute, right? Applying T star. So how do I calculate T star of this quantity? So let me pull back once more. How do I calculate T star of this quantity? Let me go back even one more. So I am interested in calculating T star of this element, right? This element is an element of the dual space W star. Is this clear? This is what I'm interested in. But how do I evaluate this? So this is an element of W star. So T star will be an element of V star, correct? I'll go a little slower if people, I mean, just stay with me. So this is an element of W star. T star is the classical dual map. So T star of an element of W star is by virtue of definition an element of the dual space V star. So how do I even evaluate this element? Well, I have to evaluate this at an arbitrary vector little v. Little v is an arbitrary vector. So this is an element of V star. I evaluate this on V. But what should that be? That should be this quantity. So this is just to indicate that the inner product is with respect to W and not with respect to V. If you are confused, ignore that. This acts on TV, right? That's how you evaluate the dual. But what is this? This quantity is nothing but TV dot W, correct? By definition. Okay? But if you think about it, so I want to write this as I want to, yeah. So
How that is the case, I did not understand.
which one?
How, I mean, dot W evaluated at TV, how that is TV comma W. This
Yes. Well, so that is, yeah. So that is what we said, right? So when you have dot W, this is a map from W to R. So how is this map defined? W prime goes to, right?
okay, so notation was confusing me.
Yeah, no, I know. I know that the notation can be confusing. There are a lot of stars floating around. That's why I'm saying that I'll try to go slow, but it's not something difficult. You have seen much difficult things in the course. You just have to sit down and pay attention to which is which and what does the definition entail. So here, by virtue of the definition, this map acting on a vector of W means you dot this input vector with this little w, which is just this. And so the point is we're trying to understand what is this element. How do I understand an element in the dual? The only way to understand an element in the dual is to evaluate it on all vectors of the original vector space. So that's what we're doing. Evaluate on all possible little v. So that will give us this. Okay. So that's the first two steps. Now I'll go back to the slide, but are there any questions so far? We're trying to unravel what is T star of this particular element of W star by the finite dimensional Rees representation theorem. Every element of capital W star is of this form. We just proved it. So it suffices to know what is T star of such an element, because every element of W star is of this form. Okay. Okay. So this is this. So by definition, this is PV dot W, and again I'm keeping the subscript capital W here because I want to keep track of the inner product in W versus the inner product in V, because there are two inner products floating around. But now I'm saying this is the same thing as take T of this thing acting on V. So think of it this way. What is this quantity? So I'm saying this is something which is there. T of dash comma W. Think of this as a linear map from V to R. Well, it is a linear map. Given any V, I just plug it in here and then I apply TV. That's an element of W and then I dot it with W, right? So this is indeed a linear map. So this is little v, by definition, will be T of whatever you plug in, it goes to T of that, dotting with W. So this is the definition of this map. So by definition, this quantity, because it's on all V, equals this quantity. So because this is for all V. So this map, so what I'm saying is T star of this element of W star equals this element of V star. It might look a bit abstract and perhaps a bit confusing, but hopefully as long as the logic is clear, you're totally certain what inner products go where and what is happening. At least make sure the logic is clear. Don't try to get confused with the geometric picture versus the logic versus what's going on. Follow the logic so that you know the algebraic manipulations, and that should be watertight. So you cannot replace a vector with a linear map and a linear map with its dual. I mean, you have to identify right things at the right place. So this is a map from W to, so T star was, this was an element of W star. T star of this is an element of V star. This is also an element of V star. And I'm saying they're equal as elements of V star. And they're equal because if I evaluate both of them at the same vector, I get the same output. That's it. So are there any questions? So, and again, for those who might be almost sold on this, but you still have a bit of confusion, go back and read this at leisure, work through the brackets and so on. You should be able to see that it's, as I said, literally not conceptually hard. It's a notation which might be a bit off-putting, at least when you see it initially. Yeah. Yeah. So what did we observe? We observed that T star of this thing, remember, so T star of this thing is going to go to this particular thing, right? T of dot, that's what this goes to, right? So this is the phi W. And now I want to apply capital phi V inverse. Okay, all right. So capital phi V inverse, and again, what does capital phi V do? So the other map here basically says V goes to dot V. That is this map, right? So there is this, right? This is my capital phi V, so I want the inverse. Okay, fine. So this is what we're after. This thing. Okay. So you start with yeah. So you start with phi W, apply it to CW. Well, it's CW, but because it's antilinear or skew linear in the second slot, C bar comes out. Apply T star. T star is linear, so it's C bar, and then this is something we just proved, right? T star of this is T of dash comma W, and then you're applying phi V inverse, but phi V is skew linear, so C bar is C, and then it's phi V inverse of T of this. So the upshot is, even if you ignore all of this formulation, the adjoint is a linear map because you're putting two skew linear maps. So the skew linearity is cancelled, you get linear at the end of the day. Okay. So we will denote the adjoint of T also by T star. And this is the point of confusion for many, and you will have to get used to it. Just don't be don't be be throwing up your hand saying, okay, I mean, this is too much. This is an abuse of notation, but it's a good abuse of notation as opposed to many other abuse of notation you'll encounter in mathematics and science subsequently. This is called T star for a reason. So this is not to be confused with the T star that we are using to denote this one, for example. This is the classical adjoint. Sorry. This is the classical dual. Just dual for this thing. And it seems like we're denoting the adjoint. So this T star is a map from W star to V star. On the other hand, we have this map, the adjoint. Why don't we call it the adjoint? Well, we can. And we're saying that call this also T star.
ADG notation was already for, I mean, the determinant adjoint.
Yeah, okay, fine. So, I mean, you can just call it whatever. I mean, adjoint of T. Adjoint, whatever, just or use adjoint till, I mean, I don't mind, just use whatever. My point is that you could call it something else. We are insisting on calling it T star, and it should be clear which T star is which, because this adjoint, the domain is W. The classical dual, the domain is W star. So the domains will already tell you which one is which. So if I say T star and I say it's the adjoint, it's clear that I'm calling it T star, but the adjoint is a map from W to V. Whereas if I say the dual T star, I'll still call it T star, but being the dual means it's a map from W star to V star. So just by virtue of the domain, you'll be able to figure out which one is which. Okay. So in that sense, there is not too much confusion, but it will be explained soon enough why we're calling it T star. There's a reason. Okay. So I wanted to warn you about this because the first reaction would be, why are we calling two distinct things T star? Well, sometimes they are avatars of one another, so might as well call it T star. That's secretly what's happening here. The other reason is two things could have the same name. It's just a bad choice, but in this case, it is actually an excellent choice, as you'll see. Okay. So as I said, there should be no confusion, although they're denoted by the same symbols, because the domains and codomains are entirely different. Okay. So I'll take a pause here, and I'll probably take 10 minutes more today, since I started a bit late, because it's better to go a bit slow and then get through this rather than rush through this, because this is an important concept definitely for any subsequent things you'll do in maths or partly even in physics and linear algebra too, because this is the beginning of inner products and duals and adjoints, everything coming into play all at the same time. So, any questions? Okay. So the first thing that you should ask, or you might ask, not you should, because some people like abstract structures, is there a cleaner description of this adjoint? So we see this adjoint is a composition of three maps, and there are these two phi W, phi V's, which are nice maps, but then you have to take the inverse of another, put the classical dual in the middle. I mean, fine, all of this is there, but is there a better? Well, there is a different one. Whether it's cleaner or not, it all depends on your taste in the kind of mathematics that you like. Let's take W in W and consider T star of W. So this T star, remember, is my adjoint because my domain of this T star is W and not W star. So this is my adjoint. So by construction, this is exactly what the adjoint was, right? So T star of W was T of dash. So T star of W is what? It's an element of V, right? So this, remember, is an element of V. And this is the adjoint. And this is also an element of V. Why? Because see, this T dash is a linear map. So, I mean, T dash is essentially a linear map from V to W. So if I inner product with W, this is now an element of V star, this entire thing. Because if I give you a little V, you take TV dot W, and that's a real number. So this is an element of V star. So capital phi V inverse, this entire thing is an element of V. So indeed it has, and it's something we just showed here, right? So this is something we just showed. Put C equal to 1. Put C equal to 1, you get W. So this is what it is. Okay. So, okay, fine. So now if I apply phi V to both sides, what do I get? So this is something all of you should be able to follow. If I apply phi V to both sides, phi V composed phi V inverse is identity. So it's this. If I apply phi V to this, what do I get? So remember, what is phi V? This is a vector in V, right? So what is phi V of this little vector? It's dot. So remember, this was phi V, right? Phi V of any vector V prime was by definition dot with V prime, correct? So phi V of this is dotting with this vector, isn't it? But this is inner product. This is happening in W, and this is inner product is happening in V. That's the only thing. It's not the inner products on the same space. It's on two different spaces. So is everyone okay with it?
W out common?
Well, not quite, right? So, well, so you mean W out common how? So this inner product is now, you cannot take a vector out from an inner product.
Okay, I thought as a dot. I mean, there will be a dot there. W will come out.
Yeah, but we can in subsequently we'll see what. But the point is, even here you cannot take a W out. You can take a scalar out.
Yeah.
But the point is that this is true for all little w. So for all little w, this is saying T dash dot W is dash dot T star W. So you already realize that this is already much more powerful than this complicated expression that you had. This is literally saying that you look at T of dash comma dash dash with respect to W. This is equal to dash comma whatever this T star is. This is the adjoint of dash dash with respect to V, right? Because the point is this is true for all W, so the same W. So if I let W vary, this V is the same. I mean, this dot is the same dot on both slots. So if I have a two variable function, on the one hand I do T of the first variable comma the second variable inner product. On the other hand, with the first variable dotted with T star of the second variable inner product. But the two inner products happens on different spaces. But this is literally the identity that you're getting, correct? So this T star, this adjoint, satisfies this identity. Is this clear? I mean, this is the main identity that you should take home from this lecture, that T star, no matter how it is defined using all these phi v, phi w, at the end of the day, it has a very clean description that this T star is some linear map from W to V, which has this property that T of dash comma dash dash inner product is dash comma T star dash dash inner product. And the inner products happen in the appropriate spaces. At some point, you realize, okay, this has to be W, this has to be V. So you don't even have to put in the subscripts. Okay. Are there any questions or any clarifications, anything? So this is precisely the identity that we're going to explore in the next few slides. Okay. So, let me give you a different definition of an adjoint, which is a cleaner one. So motivated by this thing, because this is saying that we can somehow, using this phi v and phi w, construct this linear map T star, which satisfies this property that T of something comma something is something comma T star of something. So somehow there is such a map. So why don't we use it as a definition and turn it around, because this seems much clearer. So given a linear map T from V to W between inner product spaces, and declare a linear map T star going in the opposite direction from W to V, satisfying this identity. TV dot W is V dot T star W, for any V and any W to be the adjoint of T. And you notice very crucially that I'm calling it the adjoint of T, which means I'm already at the back of my mind very convinced that there is only one such map. We know that there is a map, we have constructed one, but calling it the adjoint means that you're certain that there is only one map, the map we have constructed, there's nothing else. Of course, that needs to be proven. But if you know that there's only one such map, well, it better be the one we constructed, because that definitely satisfies one. And that map, you can declare it to be the adjoint. So you can define adjoint also through this slightly better definition, that it's a map going the opposite way, so that pairing TV with W is the same thing as pairing V with T star W. Okay? At least is the definition clear. Whether such a T star exists or not is a separate story. We know it exists. Whether it's unique or not is another question. But we'll see that it is indeed unique. Okay? So, any questions or doubts? So we'll see some examples. Just bear with me for a moment. This might seem like a bit too abstract, but we'll see examples. Okay. So we have seen earlier that such a T star exists, certainly. And in fact, if you have two such maps, S1 and S2 from W to V satisfying this thing, you can check using the fact that the inner product is positive that there is a unique such map. Because see, if you have two such maps, S1 and S2, you know that TV, so what is the claim, right? The claim is that if you have TV dot W equals V dot S1 of W, this also equals V dot S2 of W, right? Because S1 and S2 are both sort of like duals, correct? Both maps from V to W satisfying one. Because they satisfy one, you get this. But now I can just look at these two. What do I get? I get V S1 of W minus S2 of W is 0 for all V and W, right? V belongs to V, but this is something very nice. This is S1 minus S2 of W is 0, right? But this is for, this is just V, this is not that, this is just V, okay? But that means what? That means I'm claiming that this implies that S1 minus S2 is, so I mean, why can you conclude that S1 is equal to S2 from here? This is for all V and all W. So all V in capital V and all W in capital W.
Since it is for all V, that means S1 minus S2 of W is 0.
Right, so we can actually plug in V equal to S1 minus S2 of W. It's the same trick that we used last time, right? If you plug in this, you conclude that norm of S1 minus S2 W is 0. This implies S1 minus S2 W is the 0 vector, but this implies S1 is identically equal to S2, right? That's why I actually did the exercise for you. The same positivity trick. So there is only one such map satisfying one. So that is even easier. We have done the hard part showing there is such a T star. In fact, we did the construction. And so you can take this to be a definition. This is much cleaner, but again, the point is if this was defined for you, you have to do the hard work to show that there is such a T star, which we did. So you have both a concrete definition of T star and an abstract definition, which then has to be proven to show that it's unique. Okay, but so this is so both have its own advantages and so on. So this is, if you like this, take it, but keep in mind that you have to do the background of why there is such a T star. Okay, so are there any questions with this definition? So they're equivalent definitions. That's what I'm saying. Okay. Yeah, so let's look at some examples. So look at the identity map from V to V. So what should be the adjoint of the identity map? Remember, the adjoint should be something which satisfies the identity map V acting on V. And again, this is V. Happening here is V dot whatever this thing is, right? And we know that whatever if you have a guess and if it works, that's it. Because it's unique anyway. So what should be your guess? So we want a map here. So that map acting on V dotted with V is, what is this quantity? This quantity is inner product BV, right? Let me ignore this V here. So this is this, right? So what is my guess for IV star of V? Any obvious guesses?
IV.
Yeah, so IV star of V, little V. So if I take IV star to be, this of course works. If I plug this in, of course it works, right? Because V dot V is V dot V. So the adjoint of the identity map is the identity map. Okay, there's nothing to check there. It's just a total. So my point is that if you can sometimes make a guess for T star such that one holds, this definition tells you that that's it, you're done. You don't have to go back and check anything else because it is unique by the condition one. Okay, so you don't have to go through phi V, phi W and do all of that hard work. Just checking one is enough. And you can check that the adjoint of C times IV, the scaling map, the dilation map is C bar. If you're working over the complex numbers, this is C bar. If you're working over the real numbers, it's still C. So this is the slight difference, that the dilation map by, say, I, for example, if you're over the complexes, is dilation. The adjoint of the dilation map by I is dilation by minus I. Whereas the adjoint of the dilation map by 3 is the dilation map by 3. Okay? Again, you can check that the adjoint of the 0 map is the 0 map, which is not a surprise, but it's good to check these basic examples. So the 0 map is mapping every vector to 0. The adjoint of that is also mapping every vector to 0. One way of checking this is the adjoint of the 0, the dual of the 0 map is the 0 map, right? So if the adjoint is defined by phi W, the dual phi V inverse, it's clear that if you put a 0 in the middle, it's a 0 map. So you can check it using the other definition as well. Okay. Now let us do a slightly more interesting example, and we'll stop after this. Suppose we have this particular map, R3 to R2, x, y, z goes to x plus 2y plus 3z, 4x plus 5y plus 6z, and this is a linear map because it's given by a matrix, in fact, right? And you can see what the matrix is. So can anybody tell me what matrix shall I write down? Should be something like x, y, z, right? Equals this. So what matrix is 1, 2, 3, 4, 5, 6, right? So T is given by this matrix. So it's a linear map. T is in fact LA, if you want. Okay? It's a linear map. So the question is, what is the adjoint T star, not the dual T star, the adjoint T star from R2 to R3? Okay? Let's see. So what are we after? So we have to compute T star of AB, correct? So we have to compute, let's put it this way, T star from R2 to R3. Okay, good. So remember, this is what we are after, right? We are trying to basically calculate. So what are we after? We are saying that T of x, y, z, AB. So this is the dot product happening in R2 must equal x, y, z, T star of AB, right? This is, so we are trying to find out this T star So this is happening in R3, this is happening in R2. Okay. So we just calculate both sides. So if you calculate the left-hand side, what is this? Is x plus 2y plus 3z plus z. So this is, if you calculate, it's a into this whole thing. So this is ax plus 2ay plus 2az plus 4bx plus 5by plus 6bz, right? Now, what is our job? So can anybody, so this is what we want, right? We want to solve for t star. So this quantity is x times the first entry, y times the second entry, z times the third entry. So what are the simplifications we're looking at here? So I want to write this as x into something. What should I write? A plus 4b, right? I want to write this as y into something, 2a plus 5b. I want to write it as z into something. Sorry, this is 3a plus 6b, right? But now can you tell me what is t star of AB?
A plus 4b, comma 2a plus 5b, comma 3a plus 6b.
So a plus, it's just reading off these coefficients because this is precisely what I want, right? I want these to be equal. So these coefficients are t star. So 2a plus 5b, 3a plus 6b. This is my t star of AB. So this is the dual. Okay, that's it. So it's very simple. I mean, this this equation 1 is sometimes quite useful. Okay, so yeah, that's the point. You write it down, you split it out, and it's this. So this quantity must equal this, which means t star of AB is a plus 4b, 2a plus 5b, 3a plus 6b. It's as if like your matrix. So if you look at the matrix of t star, it sort of looks like. So it looks like a big thing, right? 1, 4, 2, 5, 3, 6. So it sort of looks like the transpose, right? The matrix of T was the transpose of this matrix. So something is going on regarding transpose. I mean, we know that the matrix of the dual with respect to the dual basis is the transpose of the matrix of T. This is not the dual anyway. This is the adjoint, but this also seems to have a similar property. So what is going on? So let's just start with that, and then I'll maybe continue next time since it's already past 10 minutes. So are there any questions with this example? This is a very simple example, but hopefully it gives you an idea of what to calculate and what to look out for.
In this case, the inner product, I mean, both of them were very nice, so we knew what to guess. But in the case when we don't know what to guess, is there any general procedure to use?
No, not quite. So you have to use the inner product on both sides, and then maybe the expression might be complicated and so on. So it might become tedious, yes.
Because it was only one equation, and we need to determine. I mean, for example, here we need to determine 3 components, and it's only one.
Right. No, that's true. So we'll see a different approach. So if I don't get to it, we'll start with it next time. Is that you can recover T star, that adjoint, by knowing its matrix with respect to some basis. Okay. But we'll see that the basis has to be chosen with care. And so it will boil down to choosing an orthonormal basis or something of that sort. So that is what we're trying to get to. So you can actually, in theory, also compute the adjoint by saying that I know the matrix of the adjoint with respect to some basis, but that basis better be chosen to be compatible in a certain sense with the inner product. So once you do that, you can actually recover T star because you know the matrix representation of T star with respect to that nice basis. So yeah, here implicitly we are choosing the standard basis because we are saying express x, y, z as x into E1 plus y into E2 plus z into E3, right? And the EIs are an orthonormal basis of the standard inner product. So implicitly we are using all of that, although if nobody pointed this out, we'll not notice it. We'll say, okay, XYZ is XYZ. I mean, what's the basis here? The point is we are choosing E1, E2, E3 as the standard basis of R3, and it is an orthonormal basis with the standard inner product. And that is precisely the reason why the matrix of T star looks like the transpose of the matrix of T. Okay, and that is what we'll explore next time. That this basis cannot be just any basis like we did for T and the dual. It has to be an orthonormal basis. Okay. So yeah, so that's something we'll explore. But let me just finish off with this example. And this is something we have seen many, many times. So maybe some of you have got bored with this. And I keep bringing this up. Look at the trace map. So the trace map is a map from M2R to R. I want to consider the adjoint. So the adjoint is now going to be a map from R to M2R. So how do I calculate? Well, I have to calculate trace star of mu. Well, what do? I take a matrix, trace of A is a real number, I take the dot product of the real number with mu. This is nothing but A plus D times mu on the one hand, right? On the other hand, see, the point is, what do I want? I want this to be equal to A dot the adjoint of mu, right? But this is happening where? This is so this is happening in R, this is happening in M2R, 2 cross 2 matrices, right? So I'm looking for a 2 cross 2 matrix corresponding to trace star of mu, so that, but this I know already. What is this quantity? This is the inner product on M and R is trace of, let's say, I mean, it doesn't matter really. It's like A transpose, let's say, this quantity. Let's call this B, right? So it's trace of A transpose B or AB transpose, it doesn't matter. Right? This was the inner product. So I'm saying that given this quantity, I'm looking for a matrix B, so that trace of A transpose B is this. But this is a quantity we already know. It's A plus D into mu, right? So we're trying to find a matrix B so associated to mu, so that A transpose B has trace A plus D mu. But A plus D mu, I can think of it as the trace of mu times identity times A. Because identity times A is A and trace of mu times A is mu into trace of A. So trace is linear. And that's it, right? So this will work because this thing, I can think of it as, see, this is the same thing as trace of, sorry, I put the inner product there. There should be no inner product. The inner product is just trace. This is nothing but trace of AB transpose, right? Because trace is transpose invariant, right? So this all, if I compare, what do you think is B? So
Mu I2.
Mu I2, because here the transpose or anything doesn't matter. So it's just mu. So the trace star map is something very, very simple. It's a map from R to M to R. And what does it do? Given a scalar, it maps it to the dilation matrix. That's it. Okay? Very simple map. And I mean, it shouldn't be a surprise, but it's good to work out this basic example so that you have a complete understanding of what it is in basic examples. I mean, you don't have to do very complicated examples. So is this okay with everyone? I'll stop with this. That the adjoint of the trace map is simply sending a scalar to the dilation by that scalar as a 2 cross 2 matrix. And there's nothing sacrosanct with 2 cross 2 matrix here. You could do this for M and R to R. You would simply send mu to mu times IN, the scaling matrix, exactly for the same reason. Okay. So in the Viva, some of you were asked about the dual of this map. Now you can check that the dual composed with the phi V, phi W will give you this map. Okay. You can check it very easily. Okay. So yeah, so this is just this. So the trace star of mu is mu times identity. So I'll stop here. There are a couple more things. I'll do those examples next time. You can read through them anyway. The slides have been shared. Maybe I'll start with that next time and then continue from there. Okay. So I'll stop here. So if there are any questions, feel free to ask.